See, we've already studied that this time-independent Schrodinger equation is given by this expression, that is minus hk square upon twice m del square psi upon del x square plus vx psi is equals to E psi. And here E is a constant. And I know that this is a second order differential equation. So this is a second order differential equation. Okay, in fact, I can replace this like partial derivative with the total derivative also, because psi is only a function of x when we are dealing in time independent Schrodinger equation. So this is second order differential equation in x. And for finding a unique solution to the problem, what you need to find, you should have hints for psi and psi dash. So if you know the value of psi at some point, and if I know the value of psi dash at some point, then I can find my solution guaranteed. I can find a guaranteed solution. Okay. For the cases, let's say if psi is some point it is equal to 0 and psi dash is also 0 at some point equal to 0. Okay. And if potential is not even infinite, then it implies that psi must be equal to what? 0 only. Psi must be equal to 0. In fact, if potential is infinite, then it is fine. Then psi is equal to 0. But if for the 2 points, psi is 0 and psi dash is 0, then it necessarily implies that psi must be 0 everywhere. This is from theory of differential equation. Okay, so basically what I want to say that if we know something about psi and psi dash, then psi can be fully determined. Then psi can be fully determined. Okay, and as I already told that since this is a Schrodinger equation, time-independent Schrodinger equation is an eigenvalue equation. So quite often you will find that these are written as energy eigenstates or simply eigenstates. These are simply written as eigenstates or simply these are written as eigenstates or simply an energy eigenstates or eigenstate, because they are satisfying this eigenvalue equation. All the set of all allowed values of E, it is called as the spectrum of the Hamiltonian. Spectrum of the Hamiltonian H. Okay, please to understand, if you're getting confused here, don't get confused. See, what I want to say, that if psi dash is 0, it implies psi x is psi x is a constant. And if at one point you get that it is 0, then it is 0, isn't it? So psi x must be 0 from you. Don't get confused here. Okay. Somebody was remarking on this, so therefore psi x must be 0, even if potential is not infinite. So if at 2 points, let's say at 2 points, let's say x naught, at point x naught, you have these two things, that is psi x is 0 and psi dash x is also 0 at, let's say, at x equal to x naught. Now, since psi dash x naught equal to 0 means psi x must be constant, and at a point if it is 0, then psi x must be 0. So this trivial solution is the only solution in that particular scenario. For Vx equal to infinity, yes, indeed psi has to be 0. But if this is also the condition given to you, then also potential is, then also psi is 0 irrespective of potential being infinite. Okay, now let us come back to the main point. So we were discussing h cat psi is equal to E psi. Psi has to be eigenstate. Fine. Psi has to be an eigenstate. And why it is an eigenstate? Because it satisfies this eigenvalue equation. And what are these E? The set of all allowed values of E form the spectrum of this Hamiltonian H. Degeneracy, we'll say only if degeneracy exists in the spectrum exist only if more than one solution of psi x corresponding to same energy eigenvalue. So if you have more than one eigenstate having the same energy, then these states are called as degenerate states. The solutions of these psi x, the solution or these eigenstates depends on the potential. As we are going to see later on, that we are going to solve our Schrodinger equation for different potentials. Initially for one-dimensional potentials, and then we'll take the cases for the two-dimensional and three-dimensional potentials. So this psi x depends upon the potential Px. Okay. And one of the most important conditions that we are going to impose on the psi x. So we are going to take all sort of potentials, okay? Not only the potentials which are fine, we will also take the potentials which fail to be continuous, but indeed they are piecewise continuous. We will take probably potentials which are unbounded as well. Let us take, for example, half kx square. So harmonic potential as x tends to infinity, it tends to infinite. So it is an unbounded potential. Okay. And piecewise continuous means, let's say, finite square wave. So we are going to see all these things, okay? We will have some infinitely discontinuous functions like Dirac delta functions. Or we'll also have something like hard walls, that is an infinite square well or infinitely deep square well. So all these cases we are going to see. Don't worry. So we are going to take all these potentials. We are going to take all these potentials and try to find different eigenstates corresponding to all these potentials. So basically, from here on, the objective of us would be to solve the Schrodinger equation for a particular potential and try to find energy eigenvalues or energy eigenstates, like here it is, eigenstates. On the wave function, we'll impose a condition that psi x must be continuous and bounded. And as we've seen in the previous cases, even if we take hard walls, even if we take Dirac delta function, psi dash had some finite discontinuity. It will not be infinitely discontinuous. So psi dash in any case must be bounded. So psi x must be continuous and bounded. And at best, we can think that psi dash will be a bounded function. Okay, it is not unbounded anyway. So this is a condition that we are going to impose. Okay. We shall at times not use the condition of normalizability of wave function. If it is needed, then we'll do. If it is not needed, it is fine. Because understand that there are situations where psi x may not be normalizable. For example, a free particle situation we are going to see later on, there you will find that the momentum eigenstates are not normalizable. So we'll see all these cases, don't worry. Okay. Indeed, you can say one thing, that if the wave function is not normalizable, then it lacks physical interpretation. Indeed, it lacks a physical interpretation. But if we take suitable superpositions of these unnormalized states, we get some normalized solution, and which indeed represents a free particle. So later on, we'll see all these things. Don't worry about it. So right now, just keep in mind that for momentum eigenstate for free particle may not be normalizable. So therefore, I'm not writing it as an essential requirement right now. We'll do it as and when cases required. So for example, if I'm solving infinite deep square well, then I may normalize my wave function. But if it's not required, I'll not do it. Okay. So first condition very much true, that is psi x must be continuous and bounded. So, and psi dash also should remain bounded. I'm not writing that psi dash must be continuous, because we've seen that for hard walls, psi dash bears a finite discontinuity. For Dirac delta function, psi dash bears an finite discontinuity. So I'm not writing, I'm just writing psi dash must be bounded. Or another requirement from here, that is psi x must be continuous, can be that the energy eigenstate must tend towards zero as modulus of x tends to infinity. So this is a condition for bound states. So if I'm talking of a bound state, then psi x must tend to zero as mod x tends to infinity. Because otherwise the wave function will not be able to get normalized. So we can say that this is a condition for normalizable eigenstate. So for normalizable eigenstate, wave function must be such that it vanishes at plus minus infinity. Now there is one more important terminology that we'll quite often see, which is called as the orthonormality or orthogonality. Okay, so if we are discussing some spectrum of H, so if I'm operating H on psi, I'm going to get some En psi. Okay, and right now I'm considering that these are countable eigenstates, eigenvalues. Right now I'm just thinking about countable eigenvalues only, to which I can label them with N. Although it is not necessary as such, because it may be possible that for a given potential, it may be possible that the spectrum of H cap may have discrete as well as continuous part. But right now, I'm focusing on this countable energy eigenvalues only. Okay, now corresponding to all these ENs, there will be some psi-ns. Fine. So let's say solution for this is, let's say psi1, psi2, psi3 dash dash dash. Corresponding energy eigenvalues are E1, E2, E3, so on and so forth. In general, remember two wave functions are said to be orthonormal if psi star psi n dx is Kronecker delta mn. It implies that if both of them are equal, then it is equals to 1. And if both of them are unequal, then it is equals to 0. And this, in terminology of vector space, is also called as the, you can say, inner product. So this is the condition for orthonormality. Now, one more important thing is completeness. See, the energy eigenstates, that is science, are said to be complete in the sense that any wave function can be expanded as superposition of energy eigenstates. That is, if I want to write my psi x, I can always write it in terms of energy eigenstates. If I'm doing this, I'll say that my psi x is a complete wave function. Okay, this is the completeness property. That is, if the energy eigenstates are known to me for a particular problem, if I know the energy eigenstates, or if I know these eigenstates, I can write the general solution as the linear combination of these energy eigenstates. Indeed, you can Right now here I have not written the time dependence. So basically this is the solution at time t equal to 0. So at time t equal to 0, if I want to write the general solution, provided I know the energy eigenstates, then this would be the general solution. And writing this thing implies that the energy eigenstates are complete. Okay, so this is called as the completeness property. Further, if the wave function is normalized, then I know that minus infinite to plus infinite dx psi star psi must be equal to 1, and which indeed means minus infinite to plus infinite and if m is equal to n only, then it is going to yield result. That implies summation cn mod whole square, it is equals to 1. Okay, so it implies this is one important result. Let us consider a normalized wave function of a particle given by psi x is equals to n times summation n equal to 0 to infinite 1 upon root over 7 raised to power n pi n x. Okay, here phi n's are energy eigenstates corresponding to the Hamiltonian edge. So these are corresponding energy eigenstates. We want to find the value of n. We want to find the value of n. So I'm giving you a minute to attempt this, then we'll see. Okay, so as you know that I have stated that psi is normalizable, right? Since psi is normalizable, then and psi is complete in the sense that it is represented as the linear combination of the energy eigenstates here. So again, I'm reiterating the previous thing that I wrote here, that if psi is normalizable, then psi can be written as the linear combination of the energy eigenstate, let us say right now for phi, then I know that the psi star x, psi x, the normalizability would imply that my summation Cn mod whole square should be equals to 1. Because after all, these energy eigenstate phi n are orthogonal to each other. Okay, these are orthogonal to each other. If that is not written, please do write it here. So these are, I'm writing it here. These are orthogonal to each other. So these are phi n's are orthonormal energy eigenstates. Now, if I want to find this n, how would I find? So I know that psi x is normalizable, which implies that summation Cn mod whole square should be 1. And what is Cn, by the way, here? It is n square 1 over root 7 raised to power 2n. It should be equals to 1, where n lies from 0 to infinity. Okay, and would imply that n square times summation n equal to 0 to infinity 1 upon 7 raised to power n should be equal to 1. You know that this is a geometric series. Infinite terms in geometric series, when added, would give you this. So this is n square 1 upon 1 minus of 1 by 7 is equals to 1, and which would imply that n square times 7 by 6 is equals to 1, and implies that n should be equals to root over 6 by 7. The value of the normalization constant n would be root over 6 by 7. I hope it is clear. Okay, this is so remember psi x can be represented, if psi x can be represented in the linear combinations of the energy eigenstates, then we say that these energy eigenstates are complete, or this is the completeness property, psi n's. Okay, so psi n's are complete, the energy eigenstates are complete. Okay, so this is called as the completeness property. Now, let us move a little bit further and see that, and we know that already, that that I know that for all future times, psi as a function of x comma t can be written as psi as at x equal to 0 times exponential minus iota et upon h ket. Okay, so if I'm writing the general solution, what it would be? So generally, more generally, I can write this thing, that psi as a function of x comma t can be written as summation n equals to 1 to infinity bn or cn, I thought I wrote exponential of minus iota en t upon h ket times psi nx. So more generally, for all future times, I can write wave function this way. Okay, this is how you can write wave function for all future times. Okay, and understand this is an outcome of the linearity of the Schrodinger equation. So if psi1 is a solution, then psi1, psi2, psi3 are all solutions. And if I want to find at any future time, then I have to multiply this time dependent factor as well. Okay. Now, if I want to extract this Cn, how would I do? How would I do? So I'll use a technique. See, Cn would be simply equals to minus infinite to plus infinite psi n star x and simply psi x. Because see, psi a can be expressed in terms of psi n, Cn psi n, and I know that if this psi n are orthogonal to each other, if they're orthonormal to each other, sorry, for that matter, if they're orthonormal to each other, then if I expand this psi x in terms of C and psi n, then orthonormality requires me that only non-zero integral would occur if if like these both are equal. So basically, I'll use a different symbol so that you don't get confused. So m equal to 0 to, let's say, even if it's infinity, then I'll get this particular integral as non-zero, or I'll get Cn only if n is equal to m. Okay, if n is equal to m, then I'll get Cn. So understand that this Cn can be obtained from this particular integration. So if I have this psi x can be expanded in terms of linear combination of orthonormal states. And from here, it is quite evident that Cn would be then equals to this. This is something that I'm leaving up to you. You can take an integral and you can find it on your own. Now you just think about one important thing that I'm going to right now mention. See, if I'm writing what would be my psi x, so my psi x would be simply summation n equals to 1 to infinity Cn psi nx. And what is Cn? Cn is after all this, so I'll use this way. I'll write summation n equal to 1 to infinity minus infinity to plus infinity. And here, let's say I use some different symbol, dx dash. Why some dummy variable or different variable? Because otherwise you will get confused about this and this. This is your Cn. This is your Cn. Okay, this is your complete. This is Cn, and then you have the psi n. Okay, so psi x can be written this way. So what I have written again, just see psi x can be written this way. It is equals to summation n equals to 1 to infinity. So I'll write from negative infinity to plus infinity. This this dx dash I'm writing here. Okay, and this okay. Just give me a minute so that I'm too sorry. So again, just see what I'm trying to explain is that psi x can be written as summation Cn psi n x. And what is Cn? Cn is simply dx dash psi n star x dash, that is taking the conjugate of psi n, and psi x dash dx dash. Oh, I have written extra dx dash here. Okay, so this is your Cn. Fine, this is your Cn. And why I have used this x dash? So that we don't get confused between the both. So basically, I've used a dummy variable x dash here. Okay. Now psi x is Cn psi n. Now you see if I take this summation inside, because after all this summation is going over n. So what I'll do, I'll write simply psi x is equals to minus infinity to plus infinity dx dash summation n equals to 1 to infinity psi n star x dash. And remember, this integration is going over x dash. Okay, so this integration is going over x dash. So this is, see, this summation can go inside because this is being taken over n. So n equals to 1 to infinity. After all, this remains unperturbed because this depends upon x. So I can use this here, no issues. And I take this outside. Now just think about one thing. So psi x can be written as minus infinity to plus infinity dx dash. I have taken this summation inside. And you remember, it's hardly going to matter because x, it is dependent upon x. So integration is run over x dash. So finally, I can use it inside. So I have done it, taken it inside because this depends upon n. This depends upon n. So basically, I have taken these two together. That is those who depend upon n, on which the summation is running over. And psi x dash here, it does not depend upon n. I have taken it outside. Now just think about it. Psi x is equals to minus infinity to plus infinity dx dash. This is some function which depends upon x and x dash. Let us say this is k. Psi x dash dx dash is equal to psi x. Now, don't you think you are remembered of something that we've done previously? That is Dirac delta function. So if you have a function f of x, and if I'm writing here Dirac of x minus x dash, or you say x dash minus of x, because after all, Dirac delta function is what? It is symmetric. And if here I write fx dash dx dash, is it not reasonable? I mean, you can think it on your own. See, it is quite reasonable. See, you know that from filtering property, this thing equals to f of x. So from here, by comparison from the from the filtering property of Dirac delta function, it is quite evident that this kx comma x dash is nothing but is equals to Dirac function, whether you write Dirac of x minus x dash or x dash minus x, because it is a symmetric function. So Dirac of x comma x dash is simply summation n equals to 1 to infinity psi n star x dash, and here you have psi n x. So this is called as the completeness property. This is also referred to as one other form of completeness. So this relation is called as a completeness relation, as I told. Okay, so basically, if psi is written as summation Cn psi n x, so basically, wave function can be expressed as linear combination of different orthonormal energy eigenstates, that is psi n. Then this psi n satisfies a relation this. The psi n satisfies a relation this. After all, in evaluating this relation, we have used this condition. See, we've used this condition. That is, psi x is written as Cn psi n, and Cn can be written as this thing. So therefore, this is referred to as a completeness relation. This is referred to as the completeness relation. Now, just think about one more important thing. We've already done a discussion on expectation values. And we know that if I want to find the expectation value of an operator, provided the wave function is normalized, then it is equals to minus infinity to plus infinity dx psi of x comma t, psi star x comma t, a cap psi of x comma t. Okay, so this represents expectation value of the normalized state, that is psi. Now, if I find what would be the expectation value of the Hamiltonian operator, it would be simply equals to minus infinity to plus infinity dx psi star x comma t h cap psi x comma t. And what am I going to get? So just for the see, if I can expand this in terms of energy eigenstates, and I'll pay a caution that if h cat is applied to them, so h cat psi is nothing but it is equal to e psi. Okay, so if it is like psi n, it will give me en psi n. Okay, so what I'll do, I'll use some different coordinates for here. Like I'll take different variables here, otherwise they will get muddled. So what I'll do this thing. So after it is minus infinity to plus infinity dx, and you have this, I will write this as m. I will write it as cm psi m. Okay, and exponential minus iota em t upon h cat. And from here, I know this is h cat when applies to psi will give you en. So I'll write en and then summation cn. So basically it is summation c n en psi n exponential minus iota en t upon h cat. Okay, and I know for sure that this will render me a non-zero solution. So this will render me a non-zero solution only if psi m, only if m equal to n. So instead of writing all these things here, I can place one more thing at these m's, like integration is not run over them. So I'll do this thing that is summation m comma n, and I have the cm written here, and c, this star should come, and this should be 1, I think. Sorry, plus. I'm so sorry about it, because this is star after all. Okay, so basically this is star means I have to take a conjugate of it. So this is cm star cn, and then I think en is a constant. It can be taken out. All these are time dependent factors. I can also take them common out. So this is en minus of em t upon h cat. And then I have this integration minus infinity to plus infinity psi m star psi n dx. This will render me a non-zero solution only if m is equal to n. Otherwise, it will be 0. So if m is equal to n, then the expectation value of h cat would be simply cm mod whole square times em. Because if m is equal to n, then this will become 0, e की power 0 is 1, this would be 1, and this is how. So expectation value of h cat is nothing but it is equal to summation cm square times en. So this is a quantum mechanical version of the sort of, you can say, energy conservation, or you can say that this is the expected value of energy, that is the weighted sum of possible energy with the weights, the norm square of expansion coefficient. So basically the expansion coefficients are, are norm squared and times the energy. Okay, so this is an important result that you should remember. So let us consider a problem on this. So a wave function, the wave function of a quantum mechanical particle is given by psi x is equals to 3 by 5 psi 1, or you could say phi 1 here, plus 4 by 5 phi 2. Okay, so the wave function is given as 3 by 5 phi 1 minus 4 by 5 phi 2, where phi 1x and phi 2x are eigen functions with corresponding energy eigenvalue is -1, and the corresponding energy eigenvalue is -2 electron volt here, and it is -1 electron volt for this. We want to find the total energy of the particle in this state psi. We want to find the total energy of the particle in state psi. So how to do this? The expansion coefficient are to be squared. So total energy E, let me write, would be simply this is squared, this is 3 by 5 whole squared, times the energy corresponding to it is -1, plus this is squared is 4 by 5 squared times -2. So this would be -9 by 5, I think, and then there should be minus of 16 by 5 times 2. So this is 16 by 25, 25. It is minus 41 by 25 electron volt. Okay, let us do one more. Let us consider psi1 and psi2 as two wave functions which are orthogonal to each other. Let's say orthonormal to each other. And the corresponding energy eigenvalues to both of them are E1 and -E1, or let's say E and -E. On measurement, on a state psi, which is prepared using psi1 and psi2, it is prepared using psi1 and psi2. On measurement on psi, which is prepared using psi1 and psi2, expectation value of energy is found to be equals to E by 2. Expectation value of energy is found to be E by 2. Then psi1 and psi2, which can psi1, then psi can be what? Like, can it be this in terms of psi1 and psi2? What do you think would be the correct answer? Okay, so see, uh, we know that the on measurement on psi. So basically, if I measure my uh, psi, if I carry the measurement on this particular psi, that is psi written as root 3 by 2 psi 1 plus 1 by 2 psi 2, I know that corresponding to psi 1, corresponding to psi 1, the energy is E, and corresponding to psi 2, the energy eigenvalue is minus E. And if I want to find the expectation value of energy, let's say for the first case, it would be 3 by 4 E minus 1 by 4 E, which is simply equals to minus of E by 2. Sorry, plus of E by 2. So clearly this is the, so let us do one more problem. Let wave function of the particle be given by, the wave function of the particle be given by 1 upon root 2 pi naught plus iota phi 1. Here phi naught and phi 1 are orthonormalized states or orthonormal states, orthonormal eigenstates. Okay. Corresponding to phi naught, the energy eigenvalue is E naught, and corresponding to phi 1, the energy eigenvalue is simply E1. We want to find the expectation value of energy. So we know that the expectation value of energy is simply Cn mod whole square phi. But please do remember, first point is, don't forget to normalize the wave function. Okay, don't forget to normalize the wave function, because if you don't normalize the wave function, then from here the answer would come as, I think answer would be 1 upon root 2. This is E naught by 2 plus another thing that you should not forget is, don't forget that this is not Cn square. Don't forget that this is not Cn square, rather it is Cn modulus of whole square. So here, if you take iota square, then answer would come out as minus of E1 upon 1, because this is iota upon 1. So this is incorrect answer. If even if you write Cn mod whole square, then it will come as E naught upon 2 plus iota mod whole square times E1. Answer would be E naught upon 2 plus E1. Again, this is incorrect answer. Why? Because we have forgotten to normalize the wave function. So please do remember, don't forget to normalize the wave function before executing this formula, because we executed this formula only after having normalized our wave function psi. So basically, if you want to find expectation value of energy using this formulation, then first you should normalize it. So let us first normalize it. So psi x mod whole square should be equal to 1, which implies 1 upon root 2 phi naught star minus iota phi 1 star times 1 upon root 2 phi naught plus iota phi 1 should be equal to what? 1. And let's say if I multiply an a here, so this would be a mod whole square. So it would be a mod whole square would be equals to what? 1 upon root 2, 1 upon root 2. This is 1 upon 2 minus iota, this is plus 1. So it is 1. So a would be equals to what? It would be equals to root over 2 upon 3. So a is nothing but it is equals to root over 2 upon 3. So normalization constant is 2 upon 3. So now the normalized eigenstate would be, so normalized wave function would be root over 2 upon 3, 1 upon root 2 phi naught plus iota phi. Now, if I want to find the energy eigenvalue, that would be correct. So the energy eigenvalue, or the energy, not eigenvalue, energy expectation value of energy, or expectation value of this Hamiltonian operator would be 2 upon 3 into 1 upon 2 times E naught plus iota mod whole square times 2 upon 3 into 1 E1, and it would be equals to what? It would be equals to E naught plus 2E1 upon 3. Okay, so this indeed would be the expectation value of the energy or expectation value of the Hamiltonian operator in the state psi. Okay, so please do remember these word of caution. I hope you've got uh, whatever I wanted to tell you in this lecture. I hope to meet you in the next lecture. Till then, take care. Bye.